Assalamualaikum warahmatullahi wabarakatuh. So we are going to continue chapter 3, which is on the discrete time Fourier series. Okay, so let's just jump directly into the contents. So as you know, we have learned about the Fourier series in continuous time. So similar to what you have learned in continuous time, you also have the equation for Fourier series, which is given by equation 3.3 here. So you may see that the equation is given by the signal of discrete time xn is given by summation of ak, which is ak you have learned in previous class. Ak is a Fourier series coefficient, e, jk, omega n. So e, the exponential value, j, the complex value, k omega n. K is meaning that the value for the Fourier coefficient, which is you have learned that k equals to 0 is the DC term, k equal to 1 is the fundamental frequency, and k equal to 2 is the second harmonics, third harmonics, and so on. So k omega n, and you can also write it as exponential it's summation of ak, e, jk, e omega n. Means that you substitute omega n with 2 pi over n. So here is, you may see that omega n is given by 2 pi n. So omega is the fundamental frequency of the signal, and n here is given by the fundamental period. So the difference between the continuous time and discrete time is that you have the fundamental period n. Okay, so later on when you go to the example, you will see what are the difference between the continuous time and discrete time and how you need to elaborate more on the solution. So now we go to the Fourier series coefficient equation, which is ak here. So it's defined as 1 over n. So we have n, if you remember, n is fundamental period. Okay, fundamental period. So 1 over n summation of xn. So xn is actually the equation here. So remember, it's actually vice versa. It's either to find the value for ak, which is the Fourier coefficient, or you need to find the equation or the signal value for xn when you are given the value for Fourier coefficient here. So ak is given by 1 over n summation of xn e minus j k omega n. So this equation is given in the table as appendix later on in your final exam. So you can always remember this equation since you are going to do lots of practices, but also you are given this in appendix. So when k is equal to 0, this is what you have learned before. So it's a constant value, which is n1. So it's called as a DC term. Okay, and when k is equal to plus minus 1, so this one is referred to when k equal to 1 means that it's a1, and k equal to minus 1 means that it's a minus 1. So it might be some of the times that a1 and a minus 1, the value is the same, since it does not have the complex number value. So if it have only the magnitude, then a1 and a minus 1 will be the same. But anyway, you can always calculate it differently. So calculate a1 and a minus 1 separately. So this one is we call it as the fundamental component, which is the first harmonic. And for k equal to plus minus 2, which is at a2 and a minus 1, so this is called as the second harmonic. And well, you can, in general, when you have the k value for plus minus n, which is 1 minus n, which is going to be repeating every n value, so you will call this as the n harmonic components. Okay. So how to find the coefficient ak for the given discrete time period signal? So it will be similar method how to find the coefficient for ak value for the continuous time, what you have learned in the previous class. So first is that to determine the period of t for the signal itself. So what are the period of t? From the signal given, find out what are the period of t. T means that the signal is going to repeat in the same manner. So it's going to have the same cycle, right? Then the second one is that find the fundamental frequency, which is omega n equal to 2 pi over m. So this is important. Why you need to differentiate the fundamental frequency here, because sometimes the n value is given in the equation, so you need to differentiate what are the fundamental frequency there. This for this case is that we are going to look into example 2 for this example. Finally, you may evaluate the Fourier coefficient by the given formula, which is given by this formula AK. So AK is given by 1 over n summation of xn, so E minus JK. So you might see that from the first point and the second point here is that it's all the component that you need to find out, which is the period of t, the fundamental frequency, is all given by the signal. It's from signal xn. So from xn value, you know what are the xn value here. So which is the xn value is a magnitude. Take out what are the magnitude at that moment, and EJK omega n. So it depends on what are the k value at that time. And after finding or calculating the value for AK, which is A0, A1, A2, A3, A minus 1, A minus 2, A minus 3, and so on. So you will need to plot for the magnitude for the Fourier series magnitude. So the magnitude of Fourier series is given by this symbol, and also you need to plot for the phase for the Fourier series coefficient. So it's given by this symbol. So that is all the overall what you need to understand about Fourier series. To find out what are the equation for AK, or you need to find out what are the signal xn when you're given the Fourier coefficient. So this is where you need to in this slide is that to explain the difference or the similarity between the discrete time Fourier series with the continuous time Fourier series. If you see, the equation is almost similar, but the difference is that you will have the discrete time period signal is a finite series with n term. Means that the signal, if we consider, is more than n value or n sequence value of k, the value of AK will be repeated periodically. So it means that periodically it will be repeating, okay, with the same n value, right? So well, I will give you an example of this what it means by this terms. So you have an n value, so how you are going to plot for the AK value. We go to the first example. So consider the signal, which is a discrete time signal given by xn equal to sine omega n. So as you see here in this example is that they assume that, let's say that xn is a periodic with fundamental period n equal to 5. So mean that you have omega n here, which is the fundamental frequency, omega n equal to 2 pi n, and n is 5. So n is 5 here. Okay, so if you substitute omega n into this part, you will get another equation, which is you expand the equation. So find the Fourier series coefficient for xn. Sketch the magnitude and phase spectrum. So what you need to do is that you need to expand first the equation, or this equation for sine omega n. So using Euler, expand the equation. So you know that for Euler, sine omega n is equivalent to 1 over 2j in bracket ej omega n minus e minus j omega n. So you expand it, and then you may find what are the value for A0, A1, A2, A minus 1, A minus 2, and so on. And then from there, you're going to plot the the Fourier coefficient for xn. And since you have the fundamental period n value, so it means that the period or the AK value is going to repeat for n period. So let's do this exercise. I'll give you about roughly 5 minutes to finish this exercise, then we will later discuss it. Okay, so take 5 minutes to do this. Okay guys, have you finished the example? So let's go and see what the solution for example 1. So we are given the signal xn equivalent to sine omega n. So let's see what's your answer. Okay, so how to answer this is that you need to expand the equation using Euler DTT. If you remember in the midterm exam, you're given this appendix page in the last page. So similar to your final exam, you will also be given this table. So table 1 here will be the equation and of signal system. So it will be all of the equation used in chapter 1 until chapter 5. So you have the even odd component, energy signal, power signal. This one will be in chapter 1, which is you have learned in chapter 1. Convolution integral, convolution sum is the equation that you use in chapter 2. And then you have the Fourier series, Fourier transform and inverse Fourier transform, discrete time Fourier transform and discrete time Fourier transform, which is given in this equation, will be used in chapter 3. And then next will be Z transform, which is exact. And next here you see that you have the Z transform, which is on in chapter 5, and also the Euler identity. So Euler identity given here is similar like what I have taught in class, which is you have the cosine signal and then sine signal. So imagine that even though this is not similar to what I've given you in class, but it's actually the same. So imagine that y is given by omega n. So you just substitute y with omega n. So you have cos omega n equal to 1 over 2 e j omega n plus e minus j omega n. So very simple, right? So just substitute y with omega n. Similar to the sine y, so you just substitute y with omega n. So you have sine omega n equivalent to 1 over 2j in bracket e j omega n minus e minus j omega n. And also we have here the table for Fourier series, which is the one that you are using right now in chapter 3, which is Fourier series, for how to equation for xt and equation to get AQ, which is the Fourier coefficient. And you have the sin function, the equation, and cosine function, sine function, and so on. Right? So you also have the property for all of the Fourier transform property and also the Fourier series property here. So you can think this one is similar to your midterm. So you just go back home and look back at the paper. Right. We are going to try to answer for example 1. So find xn equal to sine omega n. Okay, let's go to the solution. So have you done it all? Okay, let's go one by one. So given here the question, you're given xn sine omega n naught, find magnitude of AK and also the phase of AK. Okay, so the solution to answer this is that by using Euler identity, this one. So just substitute the Euler identity for sine omega n. So as you remember just now, I mentioned about changing the signal sine omega n to Euler identity. So sine omega n is given by 1 over 2j bracket ej omega n minus e minus j omega n. So this one is the Euler identity for sine omega n, this signal. then you expand the signal, then you will get signal 1, which is 1 over 2j ej omega n minus 1 over 2j minus j omega n. Now is that you need to compare equation 1 with the general equation. So the general equation is given by this general equation. So general equation is given by xn equal to summation of k is equal to n ak e j k omega n. So if you see here is that try expanding this equation xn, the general equation. So you get a naught e j k k e j k is equal to 0 omega n plus a1 which is k equal to 1 e j k is 1 omega n plus e2 which is a2 which is for k equal to 2 ej2 k omega n plus until infinity. So you will get roughly about this signal. So if you compare this first equation with this general signal, you will actually find out that you only have the coefficient at what value, what k value. You only have the equation at k equal to 1 and k equal to 1 here, and also k equal to minus 1, right? So k equal to 0, you don't have any value for the coefficient a0, and you do not have any value for coefficient a2 because there is no k equal to 2 in the equation 1, right? So you only have a1 and a minus 1. So from here is that you can directly see that the equation for magnitude here, a0, you find out that there is no value, so a0 is 0 to 0. A1 is, you look at this comparison with this equation. Okay, you have ak, which is the magnitude, ej, so look at this, ej, k is 1 omega n. So it means that ak value is this value. So ak is this value. So ak for k equal to 1 is 1 over 2j. And for k minus 1 is minus, because you have this minus here, minus 1 over 2j for k equal to minus 1. So you have the equation here. You have if not is equal to 0, and then you have a1 equal to 1 over 2j. So you change it to the complex number, then you will have a a1 equal to 0.5 with magnitude of with phase of minus 90 degree, and for a1 you will have the value 0.5 with the phase value 90 degrees. So this one is very direct. Now you can directly plot for the magnitude and also the phase for AK. So of course here if you see you do not have the value for A2 and A minus 2, because just now you see that there's no value for K2 and K minus 2, right? This value you do not have in the comparison with this equation, right? So there's no value for K equal to 2 and minus 2. So directly from here you can draw out the signal. So draw out the y-axis, draw out the x-axis here first, and then for the y-axis, x-axis for the phase, and also next is y-axis for AK and phase for AK. Then write out for omega naught here 0, omega naught to omega naught, and then the last side is minus omega to omega, similar to the phase value. Write out the value for the x-axis. Then directly look at A naught. So A naught is at 0. So you have this. A naught is at 0. Okay, and you have phase also at 0. Then you go to A1. A1 you have 0.5. So magnitude is 0.5. magnitude for A1 is here, 0.5. Then you have the phase is minus 90 degree, right? Then you look at A minus 1. A minus 1, you have the magnitude at 0.5. So you have 0.5. And you have the phase at 90 degree. Yeah? And the rest is that just in order for you to show that there's no value for at A2 and A minus 2, so you just plot for at 2 omega is 0 for both the magnitude and the phase value, right? But again, let's look at this equation, because based on this equation is that you are given the value, you have the value of n is where you have the value of ak will repeat periodically with value for ak. So ak will be repeating ak plus minus n is the value for this value, okay, omega n. So just let's say that if we have omega n equal to 2 pi n, this value, and the n value is 5, okay. So how you are going to plot this? It's very simple. How you are going to plot is that you use the same value that you have calculated in the previous example. So you have A0, A1, A minus 1. You need to repeat the plotting for AK plus minus n. So mean that the one that we plotted just now is in the red color. In this one, there is this red color with the part that we plot just now. So now we are going to plot for a different for repeating value for plus minus n. So plus minus n is 5. So let's start at 0 value here for A0. Okay, so if it is going to repeat every n equal to 5 value, so it means that it's going to be in the advanced mode and in delay mode for 5, plus minus 5. So we have here plus 5, 1, 2, 3, 4, 5. So we have the value at 0 here. And also for this value, delay by 5. So 1, 2, 3, 4, 5, 5. So that's why you have there at this point at 5 and minus 5 is 0. And let's go to for A1. A1 is at 0.5. So at this point A1. So you have this point. So if it's a delay and advance by 5, so means that you just need to calculate, add it by plus 5 and minus 5. So just plus it 5 means that it's going to go at in advance. So 1, 2, 3, 4, 5 at this point. And in delay, 1, 2, 3, 4, 5. Right? And the next one is that we go to A minus 1. So A minus 1 is at 0.5 and so 0.5 is at this point is minus 1. So you just do the same thing as the previous done. So you just make plus by 5. 1, 2, 3, 4, 5. And also delayed by 5. 1, 2, 3, 4, 5. Okay, so this is how you plot for the magnitude for AK. For the phase value, it will be the same thing. So you just need to repeat it. So you will have this plotting using the green markers. So you have for the plus minus 5 and plus and minus 5 value. Okay, so this is how you answer for example 1. Alright, so let's go to the second example. So what we have here is, what we have here is by using the solution in example 1, find the Fourier series coefficient and sketch the magnitude and phase spectrum for xn equivalent to sine 3, 2 pi over 5 n. So you may see here that 2 pi over 5 is actually the Fourier the frequency period for the signal, which is omega n is equal to 2 pi over f. And here is that the fundamental period is given by n equal to 5, right? So if you see here in this equation part here, 2 pi over f, if you refer to the general equation, you may see that 2 pi over n. So n here is actually equal to 5. Directly we give a value. So you may need to distinguish what is the value here. For 5 is the fundamental period. So the solution to answer this is actually similar as example 1. So you need to expand the signal in terms of complex signals using Euler identity, which is ej theta equal to cos theta plus j sin theta. Right? So try to do that example. I gave you about 10 minutes. I mean, you can finish it between 5 minutes. Okay? Right. Start now. So we have finished, we are given the example 2 just now. So have you finished doing the exercise? So let's just do this very simple one actually. So by using the solution example 1, find the Fourier series coefficient and sketch the magnitude phase spectrum. So what you have here is that you need to find the Fourier series coefficient and sketch the magnitude and phase spectrum. Okay, very simple. So what you are given here is you are given the equation xn equal to sine 3 2 pi over 5n. So if you compare this equation, what you can see is that you have the value for n is actually 5. So where you can basically determine that you have the fundamental period n equal to 5 here. Okay. So what you need to do is that you need to use Euler identity to expand this equation as similar as what you have done in example 1. So in example, these are the solutions. So you have the equation here, xn sine 3 2 pi over 5n. So find magnitude ak and ak as phase value and then plot them. So very simple. So what you need to do is that you need to just write out the general equation. So general equation is given by xn equal to sine m. M is just the value or the symbol for the magnitude. Yeah? So m here in bracket 2 pi over n. So I write here that 2 pi over n is the omega. And omega is given by 2 pi over n value. And m here is actually a value equal to 3. So if I rewrite it again, you will have sine 3 omega n. Okay, so very direct. So what you need to do is that you need to expand sine 3 omega n. So thus you expand it, you expand using Euler, so you have 1 over 2j, 1 over 2j in bracket ej3 omega n. So don't forget the 3 there. So 3 indicate that k value is equal to 3. So j3 k omega n minus 2 minus j3 omega n. So what you see is that you have the value for k at 3 and k at minus 3. So this will be the magnitude for k at 3, and the magnitude for k at minus 3 is minus 1 over 2j. So now is that you take out the component or value for the Fourier coefficient. So right now directly you see that there is no receive term. So a0 is equal to 0. And then for a1 and a2, do you see any k value for equal to 1 and minus 1? No, right? So you have the value for a1, a minus 2 is also 0. And then, do you see any value for k equal to 2 and minus 2 here? No. So you have a2 and a minus 2 equal to 0. Next, you see that you have the value for k equal to 3 and k minus 3. So here is, you write out a3 is equivalent to 0.5, or you can write it at 1 over 2j and then change it to complex number. With complex number, and you will find that you have minus 0.5j, so you expand it, you get 0.5, with a phase minus 90 degree. So that one will be for A3, and A minus 3 you will get the value 0.5 with phase 90 degree. So here is that in the beginning of the question, you are given that it has a fundamental period n equal to 2, means that it's going to repeat every n equal to 5. Okay, so AK will be repeating periodically with period of n equal to 5. And this one is n equal to 5. So plot the value for AK first from this Fourier coefficient that you already calculate. So let's look at the graph here. So I have plotted the graph. This one will be the graph for sorry, there's no symbol there, so let's just change for a while. So this one will be the graph for magnitude of AK, AK, and this one will be for the phase of AK. Right, so just look at magnitude of AK and for phase of AK, and look at the graph where the plotted with red color. So A naught equal to 0. So I'm looking at this one. So you have the 0 point here. This is a 0 point. So this is 0, this is 0. So you have the value 1, 2, and so on until 8, and you have minus 1 until minus 8 here. So at 0, A naught, which is k equal to 0, is equal to 0. So I plot this one 0, and the phase is also 0. And A1 equal to A minus 1 is also 0. So you don't have any value, 0, 0, and 0 here. Okay. And A3, A2 also you have the value 0. So look at the red plotted graph. So we have 0. So which is the one here is 0. 0, 0, and 0. A3, so you have the value for A3 and A minus 0. So A3, the magnitude is 0.5. So you have at 3 here, this is 3, 0.5. Okay, and then you have for the phase is minus 90. So you have minus 90. Okay, this one don't forget to always write out the magnitude. So the magnitude will be 0.5, and this one will be minus 90. And for this one is you will have it for 90 degree, 90 degree here. So you have plot for this one. And next we go to A minus 3. So A minus 3, the amplitude is 0.5. So 3, where is 3? 3 is here. So you have 0.5, and the phase is 90 degree. 3 here, the phase is 90 degree. Okay, but if you see here, if you were plotting for the continuous time signal, then it stopped until here. But since it's a discrete time, it's going to repeat itself periodically with a period of n. So the n value that is given in this example is equal to 5. So you're going to plot again for the same Fourier coefficient value here, but with the n period 5. So let's see. So how to plot that is that we look at A naught here. A naught. So it is at 0. So when it repeat for n equal to 5 means that you need to plus 5 and minus 5. So if you have to plus 5 it, so means that you plus 5, you plus 5, you means that you move it to the left side with 5. So you have 0 here. So this 0 plus 5. So means the advance. So 1, 2, 3, 4, 5. So this one I will plot it with a different color. So this one will be at A naught, but with the n equal to 5, so minus 5. and a minus 1 is at 0, so a minus 1 is here, and plus 5, so means that advance 5, so we add 5 to this minus 1, so you will have it at minus 6, right? So we plot it here, and you have at a minus 1, at a equal to 1 here, so a 1 plus minus 5, so you have minus 4. And at E3, you have the value 0.5, so 0.5. So E3 is here. E3 is here, sorry, E3 is here. So you minus 5 to advance. So 3 minus 5 is you get minus 2. So it's this point. Okay, it's similar at a minus 2 and minus a2 is equal to 0, so you just plot it, it's at 0 here. Another one is at a minus 3. A minus 3, where is it? This one, right? So you have the red color here, so it's going to be advanced minus 5, so 3 minus 3 times minus 5, so minus 8 at this point. So this is where you have the repeating part for the advanced value at n equal to 5. So similarly, when you plot it into the delay part, which is going to the right side here, so you are going to plot for this green plotted line here. So you have at here is at 0, 0. This is what at minus 1, 1, minus 2, 2, and then this one is at 3 and minus 3. So similarly, you need to plot it for the phase value. So that one is how you're going to plot for the discrete time when we have a repeated period of n value. So it means that if you have an n value equal to 10, so it means that from here you have a 0 value, so you need to plus 10. So it means that this 0 will be at minus 10 here. Okay, minus 10 here. So read carefully the question and you will, I'm sure you can answer the question easily. That will be all for the solution to example 2. Now next, let's go to the last exercise. So the last exercise is given by a more complex equation. So consider the period signal with period n. So you're given a period n. With xn, the discrete time signal is given by 1 plus sine 2 pi over n, capital N, and plus t cos 2 pi capital over n, and plus cos 4 pi over n, and plus pi over 2. Okay, so here directly you can see that you have the fundamental, you have the DC term here, 1. And also you know that you're going to have the value for complex number because you have the plus of the phase value here. And from here is that what you need to look at is what are the fundamental period given here. So if you see here, the fundamental period which is given by 2 pi over n. Right? Let's say if the fundamental period is given by 2 pi over n, so you may see that this is 2 pi over n, this is 2 pi over n, and this one is 4 pi over n. So what it means here that you need to expand this equation so that you have a 2 pi over n, so that you have 2 dot 2 pi over n plus pi over 2. So this one will be that you have 2 omega n. Here is that you have 1, if you expand it, it becomes 1 plus sine omega n plus 3 sine cos omega n plus cos 2 omega n plus pi over 2. So this is where you rewrite the equation again as this equation, right? So assuming that you have the frequency given by 2 pi over n, then solve the equation by using Euler identity. So it looks easy, right? So let's do this exercise. So take a piece of paper, write out the equation, expand it using Euler identity, then solve for the equation, right? Since we already finished this exercise, I hope that everybody understood what is Fourier series all about. So you have then on the Fourier series for continuous time signal and also for discrete time signal. So anyway, for the final exam, the discrete time signal will be coming out. So make sure that you understand how to actually differentiate between the Fourier series for continuous time and discrete time signal. Okay. Sorry about that, so wrong color. So right now we have finished on the discrete time Fourier series representative. So now we are going to the property of continuous time and discrete time Fourier series. So anyway, since this property can be read from textbook, so do a self-reading. Please go and refer to the main textbook, which is MJ Robert Signal System Analysis using Transform Method and MATLAB, second edition, McGraw-Hill 2012. So it can be found in chapter 4, page 171 until 174. So anyway, you can always refer to any other textbook from the library. So just go to the Fourier series and you may look at the contents where they have the property of the continuous time and discrete time for Fourier series. Alright guys, so anyway, that will be all for chapter 3 Fourier series coefficient. So I think I have uploaded the tutorial for Fourier series, so go to uLearn and download the tutorials and also the solution, which is the final solution or final answer for the tutorial also have been uploaded to uLearn. Okay, so anyway, practice make perfect. So please make sure that you do your best, do all the tutorials given for chapter 1, 2 and 3. So for next week, we are going to go into depth more on the Fourier transform. So what are Fourier transform about and how does it relate to the Fourier series? Right, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.